Welcome back everyone. In this lecture we will develop the structure theory of semisimple algebras. So, we will begin with the definition of Toroidal subalgebras. So, first we will make a remark. Suppose you start with this G, which is let us say finite dimensional semisimple algebra. So, then if it actually consists only nilpotent elements, that means add nilpotent elements. Okay. If add x is nilpotent for all G, nilpotent elements. So, then using Engel's theorem, we can conclude that G must be nilpotent. So, in that case, so G must be properly containing this its derived algebra, but we already know that for semisimple algebra we do not have this information. We have G equal to the derived algebra of G. So, that actually leads to contradiction. So, that means not all elements are add nilpotent elements. So, in particularly, so we can actually if we talk about this what is called this abstract Jordan decomposition. So, there exists some element x in G such that, so this x will have its semisimple and nilpotent parts, okay, xs plus xn you can write, where this xs is the semisimple part, we can assume it to be non-zero. Now, since this G contains both its semisimple and nilpotent parts of each elements. So, in particularly this xs is an actually element of G. So, we can assume that G contains semisimple elements, that means add semisimple elements. So, if we take x to be a semisimple element xs, then look at this subspace spanned by xs. So, this is going to be a subalgebra of this G, and what is special about this subalgebra? This subalgebra consisting of only semisimple elements of G. So, this consists only semisimple elements of G, that means add semisimple elements. So, in particularly these subalgebras actually going to play a big role in the structure theory of semisimple algebras. So, these subalgebras we call them Toroidal subalgebras. So, what is Toroidal subalgebra? So, Toroidal subalgebra. So, it is a subalgebra of G dash. So, a subalgebra, let us call it so traditionally we denote it by H. So, a subalgebra H of this G is called Toroidal subalgebra if it consists only semisimple elements. If it consists only semisimple elements of G. So, we have seen that there are some Toroidal subalgebra of G. Since G is being finite dimensional, so we can actually put inclusion as order on this set of all Toroidal subalgebras. So, we can talk about maximal Toroidal subalgebras. Okay. So, we will fix such a maximal Toroidal subalgebra. So, it is a Toroidal subalgebra that is not properly included in any other Toroidal subalgebra. So, that is called maximal Toroidal subalgebra. Okay. So, we will actually fix such maximal Toroidal subalgebra. So, fix H to be a maximal Toroidal subalgebra. So, we will actually work with this H, but before that let us make one small remark about this Toroidal subalgebras. Okay. If we take any Toroidal subalgebra, so that must be abelian inside your G. Okay. So, this is a small lemma or a small observation. So, what it says, suppose H dash is actually a Toroidal subalgebra, a Toroidal subalgebra of G. So, then this H dash must be abelian. Okay. So, this is very important observation. Already by definition H dash consisting of only semisimple elements. So, it means add H will be semisimple for each H in H dash. So, add H will act semisimply on G. So, now if we prove that this H dash must be abelian, then you can see that this H dash acts on G via this adjoint action diagonalizably. Okay. So, that information we will use later for this fixed maximal Toroidal subalgebra. So, let us see how one can prove this. So, we want to prove that H dash must be abelian. So, to prove H dash being abelian, so it is enough to prove the following. Okay. So, here is the proof. So, let x in H dash and then we prove that it is enough to prove add x, okay, when you restrict to H dash. So, this must be a 0 map and this is true for all x in H dash. Note that add x is already semisimple element. So, this is being semisimple, that implies add x restricted to H dash is also semisimple. So, to prove that add x is actually 0, so it is enough to prove that it has no non-zero eigenvalues. So, we claim that add x restricted to H dash has no non-zero eigenvalues. So, how one checks this? By contrary, assume that it has a non-zero eigenvalue, let us call it A, and then the corresponding eigenvector you call it y. Okay. So, that means we have the equation of the form bracket x y equal to a y, where a is being non-zero. Okay. So, this is by contradiction. So, contradiction by contrary, assume that add x H dash has a non-zero eigenvalue. So, that means there exists y in H dash and a non-zero in C such that this equation holds. This equation can be read as follows. So, since this y is actually element of this H dash. So, since this y is element of H dash, we know that add y H dash is also semisimple. Okay. So, now if you go back to this equation and then you can read it as follows. So, this is exactly same as saying the bracket y x is equal to minus a y. Okay. So, since add y is semisimple, so given this x can be written as sum of eigenvectors corresponding to this y. So, you write y equal to x equal to. So, since add y is semisimple, write x equal to some summation x alpha, where x alpha corresponds to the eigenvector correspond to eigenvalue alpha. Okay. So, in particularly if we take this y x, then what we get, the bracket y x will leave us summation bracket y x alpha, alpha runs over some complex numbers. Okay. So, then you can see that this y x alpha is being eigen vector corresponding to the eigenvalue alpha. So, this y x alpha will be giving us summation alpha times x alpha alpha. In particularly in this equation, this alpha must be non-zero. So, whenever alpha is 0, then we get this alpha x alpha as being 0. So, that means this sum, this bracket y x should corresponds to only the sum of this alpha x alpha where alpha non-zero. But what is written in this equation, if you go back to this equation, so this is written that the bracket y x is given to be minus a y, but here you have one equation and here you have the equation 2, but both of them actually contradicting to each other, because the bracket y x is actually given to be summation all this multiple of x alphas, where these x alphas corresponding to eigenvectors different from 0. But here in the first equation, this bracket y x is given to be minus a y, where this y is clearly eigenvector corresponding to the eigenvalue 0 for the operator add y. Okay. So, this y is an eigenvector for this operator add y corresponding to the eigenvalue 0. So, that actually gives us contradiction, because the eigenvectors corresponding to distinct eigenvalues, they must be linearly independent. So, we have the equation minus a y equal to summation alpha x alpha alpha non-zero. So, this is a contradiction. Okay. So, this contradiction arrived because we assume that this bracket x y is actually nothing but a y, where a is non-zero. So, that forces that a being 0. So, that means add x restricted to h dash is 0 for all x in h dash. So, that implies h dash is abelian. So, indeed this proof tells us that any toral subalgebra must be abelian. So, now we will go back to our maximal toral subalgebra that we have fixed. Okay. We will work with that. So, in particularly this maximal toral subalgebra, so this also must be abelian. So, this is a maximal toral subalgebra of G. Okay. So, we observed that this is abelian. So, since each element of this H is actually semisimple element, so that means the add of x is semisimply acts on G. So, H is being abelian, we can see that this add x, when you restrict x in H, so this acts simultaneously diagonalizably on this G. Okay, acts diagonalizably on this G. Okay, because these x's coming from this H, they all commute with each other and they consisting of semisimple elements. So, now we use this action of this add H on this G and then try to understand how this G splits in terms of this generalized eigenspaces of this action. Okay. So, let us look at that. So, since these elements add x or add capital H, okay, add H acts simultaneously diagonalizably on this G. So, look at this action on G. So, G can be written as follows. So, G you can write it as some G naught direct sum G alpha, where alpha coming from some subset phi. So, where what is this G alpha? So, G alpha for alpha given in H star, G alpha is defined to be those x in G such that when you act this H on this x, this is this add action. So, that means the bracket x h, sorry H x. So, that must be given by alpha of H x for all H in H. Okay. For each functional alpha in H star, we define this simultaneous eigenspace, which we call it G alpha. So, which is given to be those x in G. So, when you act this H on x, so that is given by the scalar alpha of H x. So, it is indeed easy exercise to see that this H goes to this alpha of H is indeed functional on this H. So, it must define element of this H star. Okay. So, that is some elementary exercise, I will leave it to you to check. So, these spaces that we consider, these G alphas, so they are called root spaces. So, this G alpha whenever it is non-zero and for those alpha in H star different 0. So, they are called root spaces and we collect those set of roots. So, we call it capital pi. So, what is our capital pi? So, this is those alpha in H star different 0 such that this G alpha is non-zero. Note that G is being finite dimensional implies this capital phi that must be actually finite. Okay. So, G is finite dimensional would imply phi is actually finite. So, this is a finite subset of this H star. So, this actually indeed possesses lots of information about the structure theory of this G. Okay. We will see many interesting properties of this set of roots. So, this phi is called the set of roots. Note that this G0 which is defined for the functional 0. So, it is by definition is those x in G such that this H acts on that x to be 0 for all x in H. So, that means, so if we carefully look at it, this is nothing but the centralizer of this H in G. Okay. This is the CG of H. So, which is those element that centralizes this all elements of this H. Since H is being abelian implies, so H is abelian implies this H must be contained inside this G naught which is CG of H. So, later we will prove that H must be equal to its centralizer. Okay. So, that is actually one of the important property of this maximal Toroidal subalgebra. Okay. So, later we will prove that H is indeed equal to this CG of H. So, in particularly we have the following decomposition. So, which is called either root space decomposition or Cartan decomposition. So, this is called Cartan decomposition. So, the Cartan decomposition is obtained by acting this maximal Toroidal subalgebra on this G. Okay. It acts simultaneously diagonalizably. So, then look at this common eigenspaces for the action of H. So, then you just collect them together. So, that is what gives us this Cartan decomposition. So, G is written as CG of H direct sum G alpha alpha in phi. So, this is called the Cartan decomposition or the root space decomposition of G. Like I said, later we will prove that the centralizer of this H is nothing but H. So, in particularly this G naught becomes H. So, this you can replace by H. Okay. So, to understand the structure of this G, so we need to understand what happens to the centralizer as well as this root spaces G alpha. So, that is what we would like to do now. So, before that let us make some elementary observations and then we will proceed with that. Okay. So, here is the first proportion. So, if we take this G alpha and G beta and then take Lie bracket between them, then that bracket must lie inside G of alpha plus beta. Okay. For all alpha beta in H star. So, even including 0, what we have if we take G alpha G beta the bracket. So, then this must lie inside G of alpha plus beta. So, this is the first statement. So, from this statement it is clear that if we take x from G alpha where alpha is being non-zero element, then the add x must be nilpotent. Okay. So, if x is coming from G alpha where alpha is non-zero or alpha is in phi, so then you can see that this add x, that is an element acting on G, must be nilpotent. So, this is immediate from the observation 1, because if we take this add x and then if we act it on any G beta where beta is different from alpha, or even you can include beta to be alpha also, not a problem. Then every time you apply add x and this g beta, so then you will end up inside g of alpha plus beta. So now you can only apply add x only finitely many times on each g beta, because your space is already finite dimensional. So there are only finitely many powers of add x, so that can actually take g beta inside this g of k alpha of beta. Okay. So this implies that add x square, for example, maps g beta inside g of 2 alpha plus beta, and similarly you can see that for any power I, if you take g beta, then it will map to g I alpha plus beta. But since there are only finitely many I for which this g I alpha plus beta can survive, because for various I, this I alpha plus beta, they are all distinct eigenforms. So the corresponding eigenvectors will be linearly independent. So they are all independent spaces. Since G is itself finite dimensional, so there are only finitely many I such that this G I alpha plus beta can be non-zero. So that will imply that for large I, we can get this add x power I on G beta must be 0. And now there are only finitely many betas, so you can choose again I large enough such that this add x acting on this g beta. So add x power I acting on this g itself is 0. So indeed 1 is actually immediate from 2 is immediate from 1. So here is the third statement. So now if we actually take two elements from this H star, and then if you assume that alpha plus beta is actually non-zero, so then one can prove that in terms of the killing form, this g alpha and g beta, they must be orthogonal to each other. So then the kappa of g alpha comma g beta, that must be 0. Okay. So this is again immediate from the calculations. So let us try to do this calculation one by one. So let us prove that for alpha in for all alpha beta in H star, this bracket g alpha g beta must lie inside g alpha plus beta. So let us prove this. Proof of 1. So take alpha beta in H star and then take x from g alpha and then y from g beta. So now look at what is this bracket xy. So we want to prove that the bracket g alpha comma g beta, that should lie inside g alpha plus beta. So because of that, we will compute the action of H on this bracket xy. So now using this Jacobi identity, you can see that this is exactly equal to the bracket Hxy plus the bracket x and then bracket Hy. So now because this H is coming from your H, capital H, so this Hx becomes alpha of H. So this is alpha of H x y, because this x is coming from g alpha plus bracket x comma beta of H y, because this y is coming from g beta. So this is beta of H y. So now you can see that you can take out this scalar and this scalar. So that will give us alpha plus beta of H bracket xy. Note that this alpha plus beta of H can be 0 or even this bracket xy can be 0. But anyway, this equation is true for all H in H. So that implies this bracket xy must lie inside g alpha plus beta. So that is immediate. Okay. So like I said, the fact 2 actually comes from the fact 1. So that we have already verified. So now let us verify the fact 3. So to verify the fact 3, again we take H from this capital H such that alpha plus beta of H is actually non-zero. So, because this alpha plus beta is non-zero, that is given. So, then what we do, we take x from g alpha and then y from g beta. So, and then compute what will happen to this kappa of x y. So, now we will just use this associativity and then compute what will happen to the kappa of the bracket h x y. So, you can see that this is same as minus kappa of x h comma y, and then we can use this associativity. Then we can write this is minus kappa of x comma bracket h y. So, then you can see that this is minus kappa of x comma, so the bracket h y will become beta of h y. So, this is going to be beta of h y. So, then this gives us minus beta of h kappa of x comma y. But on the other hand, so this is nothing but alpha of h x. So, this is going to give us kappa of x comma y alpha of h. So, now you put together, then what you get? You get alpha of h plus beta of h kappa of x comma y is indeed 0. Since alpha of plus beta of h is non-zero, that is the assumption that we have already made. So, that implies that kappa of x comma y must be 0. So, this proves that the kappa of g alpha comma g beta must be 0 for all alpha beta in H star such that alpha plus beta is non-zero. Then it is immediate that as a corollary, we get the restriction of the Killing form to this g naught must be non-degenerate. So, this is immediate corollary, you restrict kappa to g naught. So, then this is actually non-degenerate. Why? Because if we take some element x in g naught, which is actually inside the radical of kappa, okay, then what we get, let us say x is in g naught and that is also inside the radical. So, that means kappa of x comma y is 0 for all y is in g naught. Okay. So, then you can see that kappa of x comma g alpha is 0 for all alpha in phi, because alpha plus 0 is being alpha which is non-zero. So, we see that this g naught and g alpha that must be orthogonal to each other for all alpha in phi. So, then that implies this kappa of x comma g that must be 0 for all x in g. Okay. So, that would imply that this x is actually inside the radical of kappa. So, this implies this x is inside the radical of kappa. So, that is computed inside g. But we already know that this radical of kappa of g, that is actually when is defined on g, that is non-degenerate. So, this must be 0. So, that implies this radical when you compute with respect to g naught, that is also 0. So, that proves kappa restricted to g naught is actually non-degenerate. So, if we prove g naught is same as h, we indeed prove that the kappa restricted to this g naught, that must be actually non-degenerate. Okay. So, in some sense that is what we will use in order to prove actually this h is equal to this C g of h. Okay. So, let me recall one more important fact which is actually very trivial, but it will be repeatedly used in order to prove h is same as the centralizer of h. Okay. So, I will actually stop with this important assertion. Maybe I will continue in the next class the proof of this h is being g naught of h. So, here is the fact. So, if we take x and y from this endomorphism of V, assume that x and y commutes. Okay. So, if we know for some reason y is nilpotent, okay, so these are all given. y is also given to be nilpotent. So, then you can immediately conclude that x y must be nilpotent. In particularly the trace of this x y, if you compute, that must be 0. So, this is something very trivial to check. So, I will leave it to you to check. Okay. So, this fact again will be used repeatedly in order to prove this the maximal Toroidal algebra is same as its centralizer inside G. Okay. So, this is some ultimate goal that we will prove in the next class. Okay, I will stop here. Thanks.